40,000 kilometers is the total length of new roads built annually in the United States alone. Why do engineers choose concrete for nearly 30% of these routes? At first glance, asphalt appears easier to lay down on such a massive scale. But concrete guarantees a service life of 40 to 50 years, capable of withstanding loads of several dozen tons without deformation. But this is just the beginning. The process involves strictly calculated stages of preparation. Behind these seemingly ordinary roads lies a surprising world of advanced engineering. Roadbeds are compacted as firmly as skyscraper foundations to prevent sinking. One can notice how the soil stabilizes into a dense layer under the pressure of heavy rollers. It looks outwardly simple to pour the paving, but in reality, steel reinforcements are placed with centimeter-level precision. Massive concrete paving machines, stretching dozens of meters long, operate like industrial robots right on the construction site. They turn a pile of raw materials into a unified, durable strip. It does not end at this stage. Thus, the most durable concrete roads on Earth take their final shape. 30% of the federal highway system in the United States consists of cement concrete. While most people picture asphalt when imagining a road, one can notice the distinct gray surface dominating major routes. This material is essential for national logistics, but this is just the beginning. Why do engineers select concrete despite its rougher driving feel? The decision is not about comfort or aesthetics. Its technical superiority lies in extreme durability. Concrete roads last up to 34 years, twice the lifespan of asphalt. At first glance, it seems like a standard surface, but in reality, it resists sinking and warping under intense heat. Continuous paving machines lay the path with high efficiency. It is visible how the equipment allows crews to finish up to 3 to 5 kilometers of roadway in a single day. Speed significantly reduces project timelines. The process is only gaining momentum. The route is now ready to withstand heavy truck traffic for decades. Checking the route conditions serves as the absolute starting point for significantly reducing project timelines. After choosing where the road will go, engineers scrutinize the terrain to understand the strength and quality of the rock and soil hidden underneath. Why is such a deep analysis necessary before a single machine touches the ground? The surface often hides structural weaknesses that are invisible from above. By figuring out exactly how much dirt needs to be removed or added, the team can accurately predict how the work might affect traffic in the environment. This critical data helps them decide the best construction method, including how many lanes the road should have or how long the route will be. Once the plan is officially approved, the construction team immediately gets to work clearing the designated area. Plants are stripped away, and the roadbed is mechanically raised or lowered to perfectly match the land. The soil foundation must be compacted until it is strong enough to support the heavy concrete pavement and the vehicles that will use it. One can notice how a grader precisely levels the top layer of soil to create a flat surface. Simultaneously, essential underground systems like electricity, water, and drainage are installed beneath the future road. For routes without sidewalks, drainage ditches are built along both sides to handle runoff. But this is just the beginning. Once all underground utilities are finished, the contractor begins building the road base, which serves as the middle layer to transfer weight from the concrete surface down to the soil. First, a layer of large crushed stone is spread evenly across the ground to form the initial structure. Depending on the terrain, weather conditions, and expected truck traffic, this stone layer acts as a foundation and may be built in multiple levels. A thicker bottom layer supports a finer top layer to create a stable surface for the concrete. Compaction utilizes a vibratory roller or steel wheel roller to make sure the base remains firm and uniform. One can see how heavy rollers continuously move back and forth across the entire roadbed. At first glance, this repetitive movement looks like a routine operation, but in reality, it is critical for increasing load-bearing strength and reducing the risk of future settling or cracking. Normally, this compaction stage can take anywhere from 2 to 4 days. The duration depends heavily on the length of the road and the moisture level of the soil. One can observe a water truck driving ahead of the roller to keep the ground at the ideal moisture level during the process. This moisture helps the soil particles bind together and reach proper density under the pressure of the machines. The entire process is closely monitored by field technicians using compaction gauges and vibration sensors. Laser surveying equipment ensures all measurements stay within the allowed tolerances. Transition to the next level. After the roadbed has been fully reinforced, the crew moves on to the most important stage of pouring the concrete surface. 4 or more types of aggregates are held in reserve within the inline storage silos to guarantee a continuous production cycle. All of the concrete for the surface is supplied by an industrial batching plant, where raw materials are measured and mixed with near-perfect accuracy. Wheel loaders or conveyor belts transport crushed stone, fine sand, or gravel into individual compartments made of steel or concrete. Depending on the customer's setup, these bins maintain strict segregation of the components. But this is just the beginning of the industrial choreography. Why must the plant store materials in such isolated sections? At a casual glance, mixing the stone earlier might seem faster. However, this separation allows the calibratable belt scale system to weigh each specific type based on the preset mix design without error. The equipment measures the exact amounts needed and sends the aggregates to a large capacity feeder bucket for the next step. One can notice that the bucket is shaped to ensure all material is fully discharged, leaving no leftover residue to contaminate the next batch. It gets more complex further on. Water flows from the local supply network or on-site storage tanks into an independent weighing system. The liquid is released into the mixer via free fall or through a high-pressure pump and spray nozzles, depending on the plant's configuration. At first glance, this hydration process appears standard, but in reality, it is synchronized with the addition of chemical admixtures. Super plasticizers or accelerators are measured using a dedicated dosing system to ensure accuracy and zero cross-contamination. Once all ingredients are ready, they are loaded into a high-performance concrete mixer for rapid integration. Whether the facility uses a pan mixer or a twin shaft mixer, the internal blades drive the mass to a well-blended, high-quality mixture within a short cycle time. It is visible how the finished concrete discharges directly into the ready-mix trucks waiting below to head for paving. The transport phase demands urgency because the chemical clock is ticking. 1 to 2 hours is the average window before the concrete begins to harden and becomes unusable. Therefore, the mixing drum keeps rotating continuously during transport to prevent the mixture from separating or setting too early. Upon arrival, the truck approaches the concrete paving machine, ready to discharge the mix into the system. $300,000 is the upper investment limit for a high-end slip-form paving machine capable of revolutionizing road construction. But before this heavy equipment can begin its work, the concrete mix must be delivered to the system with absolute timing. When the truck arrives, the gray concrete is discharged into the receiving hopper of the paver using a steel chute or a powered conveyor belt. This step requires tight coordination between the truck driver and the paver operator to ensure that concrete is supplied evenly and continuously. Why is a strict rotation of mixer trucks necessary for long-distance paving? To the untrained eye, the arrival of trucks seems like simple logistics. But a continuous line ensures there is always one truck unloading while others queue up, preventing gaps or fatal delays in the paving process. In modern setups, the conveyor connects directly between the truck and the paver, which helps speed up the feeding process and significantly reduces material loss during transfer. As soon as the concrete is fed in, the slip-form paver automatically spreads the heavy mix evenly across the prepared subgrade, following the design's width and elevation. One can notice how the machine's internal auger continuously moves the mix forward, distributing the material uniformly before it enters the forming mold. At first glance, it seems like the machine merely flattens the wet mud, but in reality, it is fully equipped with vibrating pans and a slip-form mold that compact and shape the concrete while it is still wet. There is no need for any follow-up rolling or manual leveling, as the machine handles the entire formation autonomously. Built-in laser sensors, global positioning systems, or three-dimensional guidance technology ensure that the final surface stays flat, level, and aligned. It gets more complex further on. During the paving operation, the machine automatically feeds round steel dowel bars from its storage tray. It places them in the middle of the fresh concrete, right at mid-depth across the width of the road. These bars help transfer the load between adjacent concrete slabs and reduce cracking at the joints. Thanks to the built-in dowel insertion system, this step is done fully automatically without stopping the machine, even on long winding road sections. Because of its continuous slip movement, the paver leaves no cold joints between loads, creating a seamless monolithic slab that is stronger and more durable. Machines like these typically cost anywhere from $120,000 to over $300,000, depending on their size, configuration, and level of automation. With high output and extreme precision, slip-form pavers are now the gold standard for building large-scale concrete roads worldwide. Immediately after finishing, a liquid curing compound is sprayed over the entire concrete surface. This coating helps retain moisture, preventing rapid drying, and allowing the concrete to gain strength gradually. A few hours later, once the concrete begins to harden, workers use special saws to create expansion joints at regular intervals. These joints allow the concrete to expand and contract with temperature changes without cracking, preserving the surface over time. A few hours after the joints are cut, workers clean out all the dust and debris inside the gaps to prepare for sealing. They pump in a layer of special sealant, usually made of polyurethane, silicone, or bitumen, to keep water and dirt from entering the joints. Without this sealant, water could seep down through the cracks and cause peeling or damage the base layer underneath. After the entire concrete pouring and initial curing process is complete, workers begin by marking the traffic lanes with yellow paint. They place no entry signs to block vehicle access for at least 7 days, allowing the concrete to fully harden and reach its design strength. During this period, the roadway is strictly off limits to any traffic or heavy loads that could damage the surface. The process concludes with site engineers conducting a full inspection, including compressive strength tests and surface flatness assessments, before officially opening the road. Dozens of workers coordinated in real time replace the automated precision of heavy machinery in many developing regions like Peru. While concrete paving machines are common in the United States, road building here relies heavily on manual labor. Why do these projects forego slip-form pavers for simple shovels and rakes? At first glance, it seems inefficient compared to modern automation, but in reality, this method remains the primary option in remote or low-budget areas where access to advanced machinery is limited. The process begins not with sensors, but with raw concrete pouring directly from mixer trucks. One can notice how the thick mixture slides down metal chutes, landing in heavy piles on the grade. Teams immediately spread the material manually using shovels, rakes, and long screen boards. Any delay can cause the concrete to start setting before it is properly leveled, so speed is critical. But this is just the beginning. After the initial spread, workers use handheld vibrators to compact the concrete, removing air pockets to improve density. It is visible how the material settles slightly under the vibration. Others follow closely behind to trowel, smooth, and texture the wet surface using steel floats or hand rollers. Without guided systems or leveling sensors, it is difficult to achieve high precision in elevation or flatness. It gets more complex further on. Every single step relies solely on the worker's experience and on-site judgment. Therefore, maintaining consistency over long distances becomes a significant challenge. One can see how this method highlights a clear contrast between high-tech automation and traditional labor-intensive methods in global infrastructure. Thus, the finished surface awaits final conformity evaluations before officially opening the road to use. -25 to +70 degrees Celsius is the critical temperature range that the new infrastructure object must withstand. The construction unfolds in the heart of the Taklamakan Desert in China, a place often called the Sea of Death due to its extreme environment. At first glance, building a permanent highway here seems impossible due to the shifting dunes, but in reality, the project relies on massive, calculated earth-moving operations. Hundreds of bulldozers simultaneously cut down high ridges, redistributing the sand mass into lower areas to create a balanced surface. Surveyors strictly monitor the elevation and slope to ensure uniformity across miles of the open desert, while conveyor systems push excess material away from the work zone. Why is mechanical leveling alone insufficient for a solid foundation? Without a binding agent, the loose grains would shift under the slightest weight, making further construction impossible. Engineers discovered that injecting water creates a denser, cohesive layer within the sand structure. Long sprinkler arms and underground pipes spray controlled amounts of groundwater, allowing moisture to penetrate several inches deep to bind the particles together. One can notice how heavy rollers move in once the sand reaches the correct level of dampness. The constant rumble of steel drums echoes across the empty landscape as they compact the surface to remove air pockets. This process turns soft, shifting sand into a firm base capable of supporting cranes, mixers, and supply trucks. By the time the surface dries under the scorching sun, it has hardened significantly. But this is just the beginning. The stabilized sand requires an additional buffer layer of soil to ensure long-term stability. Dump trucks pour out loads of reddish earth, which bulldozers then push and level across the prepared strip. This layer adds necessary weight to the sand below, preventing the foundation from shifting under the intense heat or vibration of future traffic. Each section is evenly spread and compacted, forming a dense platform ready for the primary construction materials. Unlike the silent dunes, portable asphalt plants roar to life at the edge of the desert, heating stone and polymer-modified bitumen to nearly 170 degrees Celsius. Insulated tankers deliver the hot mix non-stop to the paving machines waiting on the line. It is visible how each paver spreads the glowing asphalt in layers about 6 centimeters thick. Steel rollers follow close behind in a tight choreography, compacting the material before it cools. Transition to the next level. The equipment switches from heavy steel drums to rubber tire rollers for the final passes. This kneading action seals tiny air gaps and creates a smoother texture, which is critical for durability. Thermal sensors on each paver track the surface temperature in real time to prevent structural defects. If the reading drops below 140 degrees Celsius, rolling stops immediately to avoid cracking once the material cools. Consequently, supervisors verify flatness with laser beams, allowing no more than 3 millimeters of deviation per meter. As the desert wind cools the surface, the asphalt hardens into a flawless black sheet, tough enough for extreme climates. Workers spray a protective seal coat, giving the road a deep shine and locking out moisture. After 4 grueling years, the 4-lane highway connects the far ends of Xinjiang, showcasing an achievement that impressed even American engineers. Two distinct approaches define the global standard for highway infrastructure. Why were the American engineers impressed by the foreign process? At first glance, the equipment appears identical across borders, but the operational scale and logistical speed create a result that commands professional respect. The engineering comparison extends from the United States to China. One can notice the uniform texture of the road, achieved by strictly following reliable technical sources and data. It looks simple to pour concrete in a straight line, but in reality, extreme precision is needed to spot any inaccurate mixture ratios before the material sets. But the work does not end with the pavement. Correction protocols are essential to ensure the long-term durability of the surface. Thus, the concrete solidifies into a permanent transport link ready for heavy traffic.